In this video, we're going to graph an equation written in vertex form and then identify its key components. So when looking at a quadratic, there are two key components that every quadratic or parabola graph is going to have. One of them is called the vertex point, and that is the point on the graph where the parabola changes direction. So if you notice carefully, there's a part of the graph where the parabola is going up and a part of the graph where the parabola is going down. And what happens is there is a point of change where this direction actually changes, and that is called our vertex point. So in the parabola that you see on the screen, our vertex point is going to be the point x is 2, y is 1, because we can see at that point we change from the graph going up to the graph going down. Then the second thing that every single parabola or quadratic function is going to have is it's going to have what's called an axis of symmetry. And it's a line drawn on the graph that basically divides the parabola in half perfectly and is a line of symmetry. It means it's the same on both sides. And if you look carefully, here is our line right here. If we flip or fold on that green line, the parabola will actually fold onto itself. And this is a vertical line that occurs, notice, when x is equal to 2. So our axis of symmetry equation line is x is equal to 2. So on every single parabola or quadratic function that we see, we're going to have an axis of symmetry as well as a vertex point where the graph changes direction. So let's practice identifying these key values for the equations that you see up above. So you can see here we have three different equations, we have three different graphs, and each has a different vertex and axis of symmetry. So let's take the time to identify them. In this first example, I see that my vertex occurs at x is -2, y is -3. Here I see that my vertex occurs at x is 4, y is 2. And here I see that my vertex occurs at x is -3, y is -1. Then from here, I also need to determine my axis of symmetry. And if I look carefully here, I notice that there's a vertical line I can draw here at x is -2. So my axis of symmetry is x equals -2. Here, my axis of symmetry is right here at 4. So I have x is equal to 4. And then here I notice, if I look right here, I have where x is equal to -3. So pretty easy to identify when we have the graph in front of us. What I hope you're also noticing is there are some really interesting patterns here that actually allow us to find this information very quickly, especially if we have an equation in front of us. So first thing I hope you're noticing is that the x values of your vertex match your axis of symmetry. So the x value of your vertex matches your axis of symmetry. This occurs because the vertex is the point that's right in the middle of the graph where we can fold it, and it will be the same on both sides because it's the point where the graph changes the direction that it is going. So that's the first pattern that I hope you are seeing. The second pattern I hope you are seeing is that this vertex point actually relates up to your equation. So take a moment and look at your vertex and your equation. Your vertex and your equation. And if you look carefully, what you're going to notice is that your vertex is actually hidden inside of this vertex form equation. So we know from vertex form that our h value inside of here is going to move the graph. It's the opposite of what we expect. So left 2, down 3. That's why our graph moved the way that it did. Well, if you look carefully, it's the opposite of our h value and our k value that make up our vertex. -2, -3. +4, +2. -3, -1. So it's our opposite of what's inside of the parentheses here with x, and then the k value on the outside. So we can actually look at a vertex form equation and identify our vertex, hence why it is called vertex form. So while we are going to graph our own functions soon, we're going to start by being able to identify a lot of the key information that we see on a graph. So on this particular graph, you can see the graph of y equals -3x times the quantity of x plus 2 squared plus 3. So we need to identify all of this key information that we see here. So the first thing I see is my vertex. I know that's the point where I change direction. So here I see that I have the point x is -2, y is 3, which matches what I expect in my equation, opposite of what's being added in there with x, and then the k value on the outside. Then our next thing is our axis of symmetry, which is the line that divides our graph in half. It's the line where if we folded, it would match up perfectly. And remember that our axis of symmetry and our vertex share that x value. So we have x is equal to -2. Then from here, we need to identify our y-intercept point. And if you forgot this from Algebra 1, remember our y-intercept is where we cross the y-axis. And our y-axis is right here. Now what's a little tricky is we can't quite see, but where this is going is it's about to hit the y-axis at y is -9. So if you were to expand that a little bit, you'd be able to see that we cross the y-axis when we hit at y equals -9, so our y-intercept point is 0, -9. Then from here, we're looking for the x-intercept points, which are where we cross the x-axis. So if you forgot that, make sure you make a note of that. And there may be a time where we have multiple x-intercepts, which is the case here. We cross the x-axis twice. So here we cross the x-axis at -3, 0, and at the point -1, 0. Now the next thing we're going to do here is we're going to determine if the vertex is a maximum or a minimum point. So this is where we're going to look at the shape of the graph itself and determine, is it a minimum or is it a maximum? So what I want you to notice here is that our graph is going up, 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 and it hits this high point here, and then it's going down. So when we say is our vertex a maximum or a minimum point, we're saying looking at the graph as is that vertex the highest point on the graph, which would make it a maximum, or is it the lowest point on the graph, which would make it a minimum? And here I notice that my point is my highest point on the graph. That's what it is, which makes this vertex point a maximum point. Then lastly, I need to determine my domain and range, and I notice that my graph is going forever to the left and forever to the right, so my domain is all real numbers. And then my range, my y values that I need to make points on my graph, start at 3, and then they go down. So my range is going to be y is less than or equal to 3. So now let's use what we've learned about vertex form to create an accurate graph and identify some of its key components. So here you can see we have an equation written in vertex form. And we know that the vertex is really hidden and embedded in that form. So if you look here, we can see that we have our h value in here with x and our k value off to the side here. Now remember, as we take our vertex out of vertex form, this h value becomes the opposite. That's why it's -h in the fancy form of vertex form. So here, this vertex point becomes x is a +2, and the y value is your k value that's out here, and it stays the same, so it's -6. And so here, I know that the middle of my graph, this vertex point, is x is a +2 and y is a -6. So I'm going to put that directly into the middle of my graph because that's the middle of my parabola. It's where I know it's going to change direction. So I have x is 2 and y is -6. Now I need to find some additional points around this because if I just plot 2, -6, I can't make a good graph of this function. And so what I like to do is I like to go out in both directions 2 points. So here, if I go smaller than 2, I could do 1 and 0. And here, if I go bigger than 2, I can do 3 and 4. So what we're going to do is we're going to take all of these x values here, and we're going to substitute them in for x in the function, and then calculate the y value that goes along with it. So if we start here with x is 0, we can just plug that in. So we would have y equals 2 times 0 minus 2 squared
minus 6. Now, you can, calculate this using the order of operations, or you can just plug this string of characters right here, this 2 parentheses 0 minus 2 parentheses squared minus 6, directly into your calculator. And if you do that, what you find is that y is equal to 2. So your calculator can be a good resource here to help you calculate those points a little bit more quickly. So now let's try x is equal to 1. And if we do that, we have y equals 2, 1 minus 2 squared minus 6. And again, if I plug that into my calculator, I find negative 4. And so now I have a couple more points that I can plot. I can see x is at a positive 2, or x is at 0 and y is at a positive 2 up here, and x is at 1 and y is at a negative 4 here. So I'm starting to see some other coordinates outside of my vertex. Then from here I can keep going and do x is equal to 3. So I have y equals 2 times 3 minus 2 parenthesis squared minus 6. If I calculate that on my calculator, I find that that one is also negative 4, which makes sense because these parabolas should be symmetrical. So this is a good check to make sure that they are in fact correct. And then finally, if we do x is 4, we have y equals 2 times that 4 minus 2 squared minus 6. And if we calculate that on our calculator, we find that that is also a positive 2, which again, x is 4, y is 2. We see that that whole thing is symmetrical. So that's a really good check that we're calculating our points correctly, and we have the correct middle or correct vertex of our graph. So there is our parabola. And now what we need to do is we need to identify this key information. So I like to just go one at a time and see what I can find on the graph. So here I see that my vertex point is this point where I change direction. So my vertex point here is 2, negative 6. Then from here, our axis of symmetry is the line that cuts this parabola in half, which goes through this vertex point here. And so what's really nice is that the vertex it kind of relates to the axis of symmetry. So our axis of symmetry line is the x value of our vertex, and it's just x equals 2 because that vertical line makes our parabola cut in half with symmetry. Then from here, I need to calculate my y-intercept point. And what we need to remember about our y-intercept point is that it is a coordinate, and it's a coordinate that occurs when x is equal to 0. So we need to calculate what y is equal to when x is equal to 0. Now sometimes you're going to have to do an extra calculation, but in this problem, it's already found for you. We can see that when x is 0, y is 2, and that is where we cross the y-axis. So in this one, we don't have to calculate anything extra. We can just identify it off of our table and off of our graph because it's where we cross the y-axis. X-intercepts, I'm going to come back to in just a second. Those are going to take us a little bit longer. But our domain, because our graph is going forever to the right and forever to the left, is simply all real numbers. And then our range, if we look at our range values, which deals with the y values of a function, we can see that the lowest y value we have is negative 6, and then the graph is going up. So we need all of the y values that are at negative 6 or larger to make this graph. So the easiest way to represent that is with y is greater than or equal to negative 6. So say we need all of these y values to make points on our graph. Then from here, we have to determine, is our vertex a maximum or a minimum? And when I look at this coordinate right here, I see that this is the lowest point on my graph, and it's going up on both sides of it. Because it's the lowest point, we know that this is a minimum point. So we've found everything here except for the x-intercepts. And the reason I kind of pumped the brakes there is because the x-intercepts just take a little bit of extra time. So for the x-intercepts, we have to remember that our x-intercepts occur when y is equal to 0. So if I give myself a little more space here, I want to make sure I transfer my equation down. So my equation is y equals 2 times x minus 2 squared minus 6. And so from here, I need to calculate my x-intercepts. And remember, those are where I cross the x-axis So it's somewhere here and it's somewhere here, but I can't tell exactly what perfect number that is. So what we're going to have to do here is we're going to have to actually calculate these x-intercept points. And because we know that the x-intercepts occur when y is equal to 0, what we can do is we can take this y value here and we can replace it with 0 and find the x value or x values that make this equation have a y value of 0. So we're going to put 0 in for y. I'm anticipating I'm going to have 2 because I can see it's crossing twice on the graph. And then we're going to solve this quadratic using what we already know about quadratic. So we're going to start by getting the part that's squared alone, because I know I'm going to have to use square roots here. So I add 6 to each side, so I have 6 is equal to 2, parenthesis, x minus 2 squared. Then from here, we divide by 2 to get that parenthesis part alone. So we have x minus 2 quantity squared is equal to 3. Then from here, to undo our squared, we need to take the square root of each side. So from here, we can take the square root of that part that's squared, and that will undo the squared. So we have x minus 2 is equal to, because we're square rooting a squared, we have plus or minus the square root of 3. And then we need to get x all the way alone, so we're going to add 2 to each side. So we have x equals 2 plus or minus the square root of 3 as our x-intercepts. Now, when we look at that, well, yes, this is a very exact answer. To me, as a person looking at this graph, it's not the most helpful answer. So while typically we leave our answers in this most exact form, when we're doing our x-intercepts, I want you to actually take your calculator and take 2 plus the square root of 3 and find what that equals with a decimal, just so we can get a better approximation of what that value is. And if I do this, I can see that this is 3.73, which, if I look at my graph, is pretty close, right? It's crossing somewhere between 3 and 4, but closer to 4. And then if I take 2 minus the square root of 3, that's going to be something very similar to that second point over here. So this is 0.27 if we round to 2 decimals. And you can see that that's very similar to what we have here. So take these values that you get when you solve using your quadratic solving strategies that we learned previously and figure out what the decimals are just to make them a little bit more helpful. So here I'm just going to write 3.73, 0 and 0.27, 0. And so now we have a pretty accurate graph as well as all of the key components of this quadratic function.